I'm sorry, the m, big M, is not which is the molar mass, is not the mass per unit um, volume, but it's the mass for a mole of a given substance. So if you think about it, this the density times Avogadro's number divided by the molar mass gives you the number of target atoms in a particular volume. Okay, and so now we have this beam which is going to be shining on this target, and so what we want to figure out is how many, given the number of target atoms per unit volume, we want to know the total number of atoms, or total number of scattering centers in the target that the beam will intersect. Okay, and it's basically just equal to this number of target atoms per unit volume times the volume, which is just the area, A, times the depth or the thickness, X. Okay, so the total number of atoms within a beam is equal to the density, the number of atoms per unit volume, times the cross-sectional area of the beam, times the thickness of the target X. Okay, and so when you plug it in from the previous view graph, you get the rho, the density, times Avogadro's number, times the cross-sectional area of the beam, A, times the thickness of the target X divided by the molar mass. Now, what we know is that in a generic way, the beam particles are going to somehow collide or interact with the target the scattering centers in the target, the atoms or the nuclei or whatever it is in the target, and are going to be deflected. Okay, and they'll be scattered into an angle, and it should be cylindrically symmetric in the sense that the scattering should be symmetric about the beam axis here. There's no reason why, like as I've defined it here, why the scattering into a particular angle theta or a particular solid angle should be, that the solid angle the scattering probability into a particular solid angle element d omega is uniform. Okay, so it can go off in any direction equally likely about the center of the beam axis. Okay, and so we can define the rate that target particles are scattered into a particular solid angle element d omega as df. Okay, this should have units of number of particles per unit time. Okay, and just generically, if again defining the differential solid angle d omega, then we have that this function here, this f, which is again the rate at which beam particles are scattered into a particular solid angle element d omega, is df d omega times d omega. So this is just generic. We've just decided to call this f, and so if we multiply the differential of this function f with respect to the solid angle, and multiply that by that differential solid angle, then we get what we're looking for: the number of particles, the rate at which particles are scattered into a particular solid angle. Okay, and if we think about it, we realize that this df d omega here should be proportional to both the intensity of the beam, that is how many particles per unit area per unit time are being are hitting the target, okay, or are traveling towards the target, okay, because if we turn that up, if we increase that, then that means that we've increased the number of particles which are hitting the target per unit time, which means that we should also so that the rate at which they're scattered should increase, and it should also be proportional to the number of target atoms that are intersected by the beam, the number of target atoms within the beam. And so df d omega has to be proportional to the intensity and to the number of target atoms, and the proportionality constant we call d sigma d omega.